Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 6.1.3. In this lesson, we're going to spend some time describing translations and using coordinate notation to determine the new location of points after a transformation has occurred, specifically with the translations. Okay. So remember, a translation is the type of transformation where an object slides into place. And so it moves horizontally, either to the right or to the left on the coordinate grid, or it moves vertically up or down. So before we get started, this coordinate notation, this is what we've already seen by using the online tool, but we've described the motion in this way. So if you took and said, let's take an object, your coordinate grid, and have it move 3 units right and 4 units down, coordinate notation would look like this. It would say that x and y changes such that x increases by 3, right? That's moving to the right on the x line, and y decreases by 4, which means it goes down in reference to the y-axis. Okay, so how could we use this, and how are we going to be using it in this particular lesson? Well, let's say that you've got a point, and that point is, say, 4, 6. Okay. So if you've got an object where one of the points or a shape or anything, it could be a triangle, a rectangle, trapezoid, anything, and one of the corners or one of the vertices is at 4, 6, and after the translation, you're going to have it at, let's see, x plus 3 would be 4 plus 3 is 7, and after the translation, y minus 4 would be 6 minus 4 would be equal to 2. So after the translation, it's moved 3 units to the right and 4 units down. This point would then move to this point here. So it's kind of, it's convenient to be able to find out the new location without actually having to create a coordinate grid and do the counting and do the plotting and move it or translate it to where it needs to go, and then looking at the coordinate grid to determine, oh, this point that used to be here is now at 7, 2. So makes it a little bit easier sometimes to have it in coordinate notation, which is why I introduced that first when we were doing 6.1.1 rather than have you write out the words. All right, so in lesson 6.1.2, you use words and coordinate points to describe how a triangle moved on a graph. These expressions described the starting place, the motion, and the point where the triangle ended up. Today, you will write similar expressions to describe transformations on a grid. All right, so let's take a look at this right here. It says Rosa changed the position of quadrilateral ABCD, here's quadrilateral ABCD, to that of quadrilateral WXYZ. How did the points, or how did the coordinates of the points change, you wondered? So the first thing for us to do is describe what type of a transformation is this. Is this an example of a translation or a slide? Is this an example of a rotation or a turn? Or is this an example of a reflection in which your shape was flipped over a line of reflection or a line of symmetry kind of a thing? Okay, so what do you think this is? And if you're saying that it is a translation, then you are absolutely right, because, and this is the key, the new image has the same orientation as the original shape. So remember, if we were to take this shape and rotate it, you would see it would change. It would go like point A would end up being over here, or the smaller side would end up being on the right or on the top or on the bottom instead of on the left. So that's what would happen with rotation. If it were a reflection, you would get a mirror image on the other side of a line. And since this is up, it's like there's no way a mirror would work this way, right? There's no image here. The image is up here, so it can't be a reflection. It has to be a translation. So now the second part is, how far did this triangle move, and in which direction did it move? So to do that, we need to look at a single point and determine, all right, it looks like it moved to the right, correct? So A corresponds to W, G corresponds to Z, C corresponds to Y, and B corresponds to X. How did each one of those move? Well, it looks like it moved to the right and it moved up. So the question is, how much did it move to the right? And how much did it move up? So why don't you go ahead and pause the video and do some counting and see if you can answer that question before I do the reveal. Did I give you enough time to count that out? I hope so. The answer is that it moved 6 units to the right, 1, 2, 3, 4, 5, 6, and 8 units up, 1, 2, 3, 4, 5, 6, 7, 8. Now, point B became point X. This point right here, I'll go ahead and highlight it. This is point B, and it became point X. So they are the 2 points that correspond to each other in our 2 shapes here. So what are the coordinates of point B and X? Name them using XY notation. So basically, since I can see this right here, X is going to be where X is 3 and Y is equal to 3, right? So this is going to be at 3, 3. It's supposed to be a 3 there. And this one is where X is 1, 2, negative 3, 1, 2, 3, 4, 5. Negative 3, negative 5 appears to be the coordinates of point B. So that's what we're going to write down here. B is at negative 3, negative 5, and X is at 3, 3. So how did the X coordinate of point B change? And how did the Y coordinate of B change? So let's take a look at this. The X coordinate went from negative 3 to positive 3. So it increased, right? By how much? And the Y coordinate went from 5. No, that's negative 5, isn't it? Oh, I didn't get that right. That's got to be a negative 5 there, right? It went from negative 5 to positive 3. So how much of an increase is that? So it says for each coordinate, write an equation using addition to show the change. Okay? So why don't you go ahead and show that process. So we just kind of discussed that the X coordinate increased by 6, right? Because it moves 6 units to the right. And the Y coordinate increased by 8 because it went 8 units up, right? So how would that look to show that as an equation? Well, we could say this, that we took the original X, negative 3, and we increased it by 6. So negative 3 plus 6 equals 3. Well, there you go. There's the 3 after the translation. And what happened with the Y? It started as negative 5, and that increased by 8. And so negative 5 plus 8 is equal to 3. So that is the coordinate, or the Y coordinate of X. So it says visualize translating this particular shape, WXYZ, 10 units to the right and 12 units up. So, we can't actually show that on the coordinate grid because it's going to go off the coordinate grid. So this is one of those situations where it's handy to use coordinate notation. So where will point X, which is currently at 3, 3, where is that going to end up after moving this 10 units to the right and 12 units up? Go ahead and see if you can figure out what the answer is going to be, and then I'll give the reveal for how we would show the coordinate notation. Okay, I'll pause for a little bit, and you do a little bit of calculating in your head to see if you can figure out where they would end up. All right, so let's take a look and see what I've got here. So this is the coordinate notation for this situation. Each one of the ordered pairs make up this particular shape, and let me just tell you, there are an infinite number of ordered pairs in here, but we're only going to focus on the ones that are at the vertices because those are the ones that are easy to identify. And we could just take one of them and find out where the new location is going to be. We can do it for all of them if we want to, but in this case we're just going to take point X. So if it's moving 10 units to the right, then that means we're going to take the X value, which is 3, and increase it by 10 because it would move 10 units to the right, following along the x-axis, and so it would stop where x is equal to 13 on the x-axis. And on the y-axis, it's going up 12, so we would start at 3 and go up 12, and so that means it's going to reference 12 units up the y-axis, starting at 3, stopping at 15. So this particular point after the translation is going to be sitting where x is 13 and y is 15. All right, so Rosa translated a different shape on a grid. Use the clues below to figure out how her shape has moved. So the 0.47 was translated to 32, -6. So we know it's a translation, correct? So that means it's going to, x is going to increase by a certain amount and y would increase by a certain amount, or x could decrease by a certain amount and x could decrease and y, they could both increase and decrease. So in this case, what appears to have happened? It looks like x values went from 4 to 32, and the y value went from 7 to -2. So without graphing, can you describe how the shape has moved? Did it go to the right or did it go to the left? Did it go up or did it go down? What do you think is the case here? Well, it went to the right, correct? Because it increased. It went from 4 to 32, so it increased by 28 units, which is going in the positive direction, which means it's moving to the right on the x-axis. And it went from 7 to -2, which means it went down. And to go from 7 to -2, that's going down 9 total units, right? Because it takes 7 units just to get to 0, plus another 2 units to get to -2. On another point, her original shape was at -16.9. After the translation, where did this point end up? Okay, so let's go ahead and use the same strategy that I showed here, using coordinate notation to figure out where the new point would be after the translation we had here. Okay, so this is defining the translation. So go ahead and see if you can figure out where the new point would be according to this translation information right there. Okay, so just to make it clear, this would be the coordinate notation, right? So every single point on this shape is moving to the right 28 units. So the x value will be plus 28, and it's going down 9 units. So the y value will decrease by 9. Okay? Take a couple more minutes or a couple more seconds to think about that and see if you got the right coordinate. I'll pause again. All right, so we need to take the -16 and add 28 to that, and we need to take 9 and take away 9 from that. So what we end up with is the new x value has to be 12, and the new y value has to be 0, which means that this point that started at -16.9 now sits at 12.0 after this translation. All right, now let's take a look at what Rowan is working with. Rowan transformed quadrilateral CDEF below to get the quadrilateral PQRS. Describe how Rowan transformed his quadrilateral. Was this a translation? Did it slide to the right? Was it a rotation, so it turned either clockwise or counterclockwise? Or is this a reflection where you get a mirror image and the new image is crossed over a line of reflection? What does this appear to be to you? I would say definitely not a rotation. It does not look like this line here. It's the longest line, and this is the longest line, so it did not go around at all. If it did, you would have to say it went around 360 degrees, which means it didn't go anywhere. So it's not that. Even the two shorter sides are here. They look the same. The only thing that I'm noticing is this guy looks like it corresponds to that guy because they have like the same level of steepness to their slope of their line, even though this one would be a negative slope and that would be a positive slope. And the same can be said for CF and PS. So this appears to be a mirror image of that. So I would say that it is a reflection, and it reflected over the y-axis, which is where x is equal to 0. Okay? The explanation is the fact that it appears to be a mirror image of the original. So Rowan noticed that the y-coordinates of the points did not change, right? If you were to take a look at this, let me go ahead and jot these in, just a couple of them. If you look at, this is the original, and this one appears to, actually I'll do D. This one appears to be at -1,5, and Q appears to be at positive 1, 5. So he is saying that it looks like the y coordinates did not change. They both stayed at 5, right? These guys stayed at 5. These guys stayed at where y is equal to 1. But the x coordinates, something happened to them. What appears to be happening with the x coordinates? What do you notice? Go ahead and give you a second to think about that. All right, so what appears to be happening with all the x coordinates? You can kind of see it here. Point B was negative 1, 5, and its image after reflection was positive 1, 5. Point E was negative 3, 1, and after reflection, its image is at 3, 1. Point F was at negative 6, 1, and after reflection, it's, wait, is that, no, that's not right. Hold on for a second. Mistake alert, hold on. All right, that's been fixed. So sorry. It's point R that is the image of E, and R is at 3, 1, and F, which started off at negative 6, 1, became point S, which is at positive 6, 1, and then point P is a reflection of point C, and point P is at 7, 5, where C was at negative 7, 5. So I think what we've got going on here is every single x coordinate is changing to their opposites, where the y coordinates are staying the same. So can you describe the changes to all the x coordinates with addition like we did in the previous problems with translations? And the answer is no, you can't. This is not a situation where you would add the same number to C to get the coordinates of P and the same numbers to P to get the coordinates for Q. This is not a translation, so that type of a situation with the coordinate notation does not work. In this case, you would have to show it by multiplying the x coordinate times negative 1. So this technically is the coordinate notation whenever you reflect an object over the y-axis. Okay, now here's one of the reasons why I don't focus on this particular coordinate notation for reflections, because it only works in one situation. The one situation where you would use that is when your line of reflection happens to be y-axis. It will not work if your line of reflection is y is equal to 1 or y is equal to 2 or y is equal to 3. And it will not work if your line of reflection is the x-axis, or x equals 1 or x equals 2. Wait, hold on. I'm messing up here. Sorry. Oh, let me go back here. It is not going to work if you've got y is equal to 1 or y is equal to, no, if x is equal to 1 or x is, I think I did say that. Maybe it wasn't a mess up. Okay. And it's not going to work if you've got a horizontal line of reflection either. It only works for this one particular line of reflection. So it's not really something worth memorizing, to be honest with you. But it's an interesting idea that happens. What parts of quadrilateral CDEF are the same as quadrilateral PQRS? How can you show that the corresponding angles are the same measure and the parallel sides remain parallel? Well, you can kind of see here that in all of these shapes, the corresponding sides are equivalent to each other, have the same measure. So line CD is the same as line QP. Line CF is the same as line PS. Line FE, or line segment FE, is the same as line segment RS, and line DE is the same measure as line QR, or line segment QR. So those corresponding sides are equal to each other, which means that these two shapes are congruent to each other, which means that we're talking about a situation that involves a rigid transformation. All right, now imagine that Rowan had reflected quadrilateral CDEF from problem 20 across the x-axis instead. What do you think would happen to the coordinates in that case? Okay, so first visualize how the quadrilateral would reflect across the x-axis, where y is equal to 0, right? The mirror would be that line right there, and so this guy would have to reflect Let's go ahead and reflect it up and down. It would have to reflect somewhere around here, right? Doesn't that look like the mirror image? And remember, when you've got a reflection, all of the points on the reflection are the same distance away from your line of reflection as the original. So if this takes 1 unit to get there, it'll be 1 unit across. If this takes 5 or 6 units to get there, in this case it's 6, it'll take 6 units to get across. Okay, so set up a 4-quadrant coordinate plane on graph paper and plot this on the coordinate plane. Okay, then do the reflection as I show it here. Then I want you to identify what are all of the points. Okay, go ahead and take some time to draw this. You don't have to draw on this one right there. Just go ahead and take the original C, D, E, F, find out what their coordinates are, and then go ahead and do the reflection across the x-axis, and then label in what those 4 coordinates are after reflection. All right, so let's take a look at this. You got point C, and I'm going to show you a little bit of, oh, no, what are they saying? They're saying that we want to relabel this where, okay, let me go ahead and put this in there, and I'll do it with nice small lettering. It said point C is going to become point J. Point D is going to become point K. Point E is going to become point L. And point F is going to become point M. So this is now quadrilateral JKLM. So what are we noticing here about these points? Well, point D is at -1, 5, and point K is at -1, -5. Point E is at -3, 1, and point, what have I done? What have I done? Hold on for a second. All right, it's always good to label things correctly. Okay, so C corresponds to J, right? Because these guys are the farthest away, farthest to left, and farthest away from the line of reflection. M and F correspond to each other. D and K correspond to each other, and E and L correspond to each other. So E, which is at -1, 5, corresponds to K, which is at -1, -5. E, which is at -3, 1, corresponds to L, which is at -3, -1. F, which is at -6, +1, corresponds to M, which is at -6, -1. And C, which is at -7, +5, corresponds to J, which is at -7, -5. So what do you notice is happening here? Are you noticing that the X values are staying the same, but the Y values are changing to their opposites? Because that's precisely what is happening here. And so if you were to use or describe this using coordinate notation, you would say that the X and the Y values change such that X stays exactly how it is, but Y changes to its opposite. Okay, so once again, just like with the previous situation, this only happens though when you reflect over the x-axis. So this isn't like something that is a go-to kind of a coordinate notation anytime you have a reflection. It only works in one circumstance, and that's this one where you're reflecting over the x-axis. All right, so now we've got a problem where Rowan noticed that, hold on for a second. In problem 620, Rowan noticed that multiplying the x coordinates by -1 reflects the shape across the y-axis. Test this strategy on a triangle formed by the points where A is equal to -3, 5, B is at 1, 2, and C is at 0, 8. Before you graph, multiply each x coordinate by -1. What are the new points? Okay, so please go ahead and copy these down. And I want you to change each one of these coordinates such that you change x to its opposite, but y stays the same, okay? Go ahead and take care of that right now. Go ahead and pause and get this taken care of. Okay, so we're going to start with the original 3. A was at -3, 5, B was at 1, 2, and C was at 0, 8. So after transforming this through a reflection, you are now going to have second point A. And we're going to label that as A, the first image of A. This will be the first image of B. This will be the first image of C, and we'll designate it that way by putting that little tick mark there. Okay, so we're going to keep all of the X or all the Y values the same, but all the X values would change to their opposites. So the new points of our image should be at 3, 5, -1, 2, and 0, 8. Okay, so now what I want you to do is I want you to take the original 3 points, point A, point B, and point C, and I want you to plot them on a coordinate grid. And then I want you to do the reflection and see if you don't get, after reflecting each one of these points, if you don't get these as the new vertices of your triangle after reflection. Okay, this is an interesting kind of reflection now, and we'll talk about it in a second. Okay, so go ahead and plot the original and try and plot the new one after reflection and see what you notice there. Okay, this is what you got for the original. A is at -3, 5, B is at +1, 2, and C is at -0, 8. So what we have to do whenever we do a reflection, right? The line of reflection is the y-axis, correct? We are reflecting the shape across the y-axis. So what we're going to do is we are going to take every one of these points and we're going to go perpendicular to our line of reflection, right? So go in a horizontal direction until we get to our line of reflection. And this takes 1, 2, 3 units to get there. So we're going to go 1, 2, 3 units across. That's how mirrors work. That's how reflections work. Your reflection is always the exact same distance from your line of reflection or from your mirror as the original object was. Now that might be something interesting for you to do, is go home, or if you're already at home, go to the mirror in your bathroom and hold up a pencil. If you touch the pencil to the mirror, it appears as if your reflection is also touching the pencil to the mirror. And if you hold your pencil 5 inches away from the mirror, the reflection is going to look like you're holding the pencil 5 inches away from the mirror itself. So that is the rule. So point A moves 3 units to get there, 3 units to get across. Point B moves 1 unit to get there and 1 unit to get across. And point C is on that line, so it actually is going to stay on it because it doesn't have to move anywhere toward the line of reflection, so it's not going to move anywhere away from it. And so now when I plot these points, I'm going to plot those 2 points get connected, those 2 points get connected, and these 2 points get connected. And that is a reflection of triangle ABC across the y-axis. Now, here's something where when you were working with coordinate grids, we can do this, whereas if you're working with a mirror, there's no way to go through the mirror into that parallel universe of your reflection. But it can be done on a coordinate grid. So let's check to see that our coordinates are correct. This point here is at 3, 5. Does that agree with what we said it was going to be here? Yes, it does. This point here is at -1, 2, and that agrees with what we thought it was going to be when we used our coordinate notation. And then C is in the same location as it was before at 0, 8. That's what we thought it was going to be. So did your triangle get reflected across the y-axis? And the answer is yes, it did. How many more do we have to go here? No, we got 1 more. All right, so this is just something for you to record into your journal. No more problems to solve. In the last 3 lessons, you have investigated rigid transformations, okay? Key is on rigid, which means unchanging, okay? These are reflections, rotations, and translations, okay? What happens to a shape when you perform a rigid transformation? Do the lengths or angles in the figure change? The relationships between the lines, you know, whether they're parallel or perpendicular to each other, do those change? Why are they called rigid transformations? Well, I kind of stated it already. Rigid means unchanging. So with all rigid transformations, you've got two conditions that are always met. All the shapes stay the same shape and same size, and you may recall us discussing the term congruence in either 6th or 7th grade. Congruent shapes are always the same size and the same shape. And they can do one of three things. They either rotate, reflect over a line, or slide to a new location. Okay, so all rigid transformations have this in common. They always stay the same shape and the same size, and the transformations are either going to rotate, reflect, or slide. Okay, so once you get this written into your journal, we are done. We've got one more lesson to do, 6.1.4, before we review on a study guide and take the first chapter 6 test, which we are going to do before we leave for winter break. Okay, so go ahead and pause it if you are not writing this in, so that you can get it done. You can copy it done. Take care. Bye.
Hey, feeling good, like I should. When in dark, walk around the neighborhood. Feeling blessed.